So now let's compare methods and let's really dive into the pros and cons of each one. So what I'm showing here is a paper by Nichols and Hayazaka. What they did is they collected a number of studies. For each study, they looked at the degrees of freedom of that study, the number of voxels, the smoothness in 3 dimensions, so dimension X, Y, and Z, the number of results. And then, given all this, they look at how high is the threshold for each of a number of family-wise error corrected threshold. So this would be, the first one would be a random field theory, Bonferroni, the Hochberg and Seeduck. These are just, if I remember correctly, this is a step down Bonferroni and this is a step up Bonferroni. De facto, they're almost always the same. And finally, this is a permutation analysis. So what you're seeing here is the threshold, the T threshold for a voxel to be, or a cluster to be considered significant. And so what is interesting here is that if you look, there's a relationship, there's a strong relationship between degrees of freedom and in the case of the random field theory, the threshold. Particularly at very low degrees of freedom, it's clear that the random field theory approach becomes hyper conservative. You would need to have, for these degrees of freedom, granted, it's not something we would usually do, but for this, you would need a peak height of 4,701 as a T value. And then, of course, the more and more degrees of freedom you get, the smaller it becomes. Bonferroni is fairly similar. It also has a very high threshold at low degrees of freedom, and slowly, the more degrees of freedom, the more it decreases. As they remark, Hochberg and Seeduck are pretty much equivalent to Bonferroni most of the time. But it is the case that the permutation analysis always gives you a smaller threshold. And it's not necessarily directly proportional to the degrees of freedom, as you can see here. For example, the threshold for the 9 degrees of freedom just happens to be lower than the threshold for the 11 degrees of freedom, sorry. But in general, the permutation approach always gives you smaller critical T values, which also means a more sensitive analysis. Now, Wu and colleagues published what I think is a very influential paper, the gist of which is do not do cluster correction, but more on that in a moment. And see, they thought, look, obviously, cluster correction is advantageous over voxel level correction, whether you do it with a Bonferroni or with a random field theory, because it is less conservative. However, it really does lack specificity if you do a cluster level analysis. And see, if you think of it, the cluster level p-value is the probability of obtaining a cluster of at least, that certain size under H0, right? So of that certain size or more under H0. So this means that when you reject the null, what you're actually saying is that there must be at least some signal present somewhere in that cluster. It's not a very specific claim. You don't know which voxels exactly inside this cluster are the significant ones. And so the problem with this is that if you use a very stringent cluster determining threshold, in other words, if you set your z-stat, your z threshold very high or relatively high, it will turn out to be somewhere close to 3.1. The size of the clusters that you get is pretty small, meaning that those clusters tend to be contained within one area. And so you can still make, even if you don't know which voxels exactly are the significant ones, you can still say, well, the cluster fell in area such and such. So you can make a pretty reasonable, a pretty localized anatomical claim. On the other hand, if you use a very liberal threshold, which means if you use a very low cluster determining threshold, so a low Z value, then the clusters that you get can actually end up spanning many different anatomical regions. And if a cluster spans many different anatomical regions, because you don't know which voxels inside the cluster are the significant ones, you can't really make any localized claim, right? So the problem, as they say, is that finding activity in the insula or the striatum, because your cluster includes both the insula and the striatum, and you don't know which are the significant voxels, it just doesn't help that much. On top of it, they also feel that because we usually show these colored maps and we color the whole cluster, we don't just color the significant voxels inside the clusters, which we don't know which one they are, it does invite the reader, and I agree with them, it does invite the reader to infer that all voxels inside the cluster are significant, which, as I said, is not the way. So here's one example that they give. They just took a previous study of theirs, and they re-thresholded it with a lower threshold, with a more permissive threshold. And so what they end up having is two big clusters. One cluster is the one that you see here highlighted in red. Here, 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 there, and there. And notice this cluster spans the insula. Right here, some of the, I guess, anterior temporal lobe right there. Then it goes, then it goes up into the sort of insula, but it also goes to the back of the insula, the posterior part. Then it spreads into the frontal, looks like the probably middle frontal gyrus. Then still middle frontal gyrus plus some part of parietal lobe, right? And again, parietal lobe and yeah, probably middle frontal gyrus. So this cluster is spanning several different areas. In fact, if you look down here, you can see in blue one of the two clusters and in orange the other cluster. Look at the blue cluster. It spans the supramarginal gyrus, sensory motor, the opercular part in the, I guess, of the inferior frontal gyrus, ventrolateral prefrontal cortex, insula, and thalamus. And you don't know, oh, actually, it also includes the SMA, cingulate, parts of the midbrain, and cerebellum, and the lingual gyrus. And you don't know, this is the cluster, but you don't know inside the cluster which are the voxels that are suprathreshold. So it's hard, right? You look at this and you might be tempted to say, oh, we found activation in sensory motor, in SMG, in opercular, in insula, in VLPFC, in thalamus, et cetera, et cetera. But that's not necessarily what your analysis is, or your result is saying. So in this sense, if you use low cluster determining thresholds, it becomes very problematic, right? Because you get these giant clusters. In fact, you necessarily get giant clusters. And the giant clusters don't allow you to make anatomically specific claims. Here's a simulation example of exactly this. So what you're seeing here is on the x-axis, the different thresholds that you could use, the different primary thresholds that you could use to create clusters. What you're seeing on the y-axis is how smooth the data are. And see, the point of this is to try to show, simulation-wise, just how big of a cluster would you usually expect to give at different thresholds for different amounts of smoothness of the data. So what the little dashed lines that you're seeing are actual levels of smoothness of real data from prior papers. In fact, these data are taken from the Nichols and Hayazaka table that I just showed you a couple slides ago. For example, let's say that your study just happened to have an intrinsic smoothness of about 8 voxels. If you had 8 voxels, and if you used a threshold of 2.3 to create the clusters, so remember using the random fields theory approach, if you put your threshold at 2.3, given that smoothness, how big of a cluster would you usually expect to get? So if we have this amount of smoothness and we use exactly 2.3 right here, it means that the size of the cluster that we'd expect You can read it out if you keep going in this sort of cyan band. So if you keep going, we're somewhere here. So somewhere around 1800 voxels, or about a little less maybe. So if you use a threshold of 2.3 to create the clusters, you would expect on average for that amount of smoothness to have clusters of just about 1800 voxels. At a voxel of 3 by 3 by 3, 1800 voxels is a pretty large volume. It's unlikely to span only one part of the brain, one anatomical part of the brain. So at this lower threshold, it's very unlikely that you will span only one area. So in other words, you'll be left saying, well, my cluster spans, frontal cortex and some parietal cortex or something of that sort, or some proximal regions, and you won't know where is the actual which of the two is the actual activation, or maybe both, but you won't know. Because again, within the cluster, you don't know which exactly are the significant voxels. On the other hand, if you used a threshold of 3.1, so that would be a 0.001 p-value, then if we do the exact same thing, so at a smoothness of 8, right here, so it means we're inside this band, this dark blue band right here. So you would expect to have somewhere around 500 voxels. So if you have a very stringent threshold, you get a cluster size of 500 voxels, probably just about the size of one, perhaps slightly larger, anatomically coherent part of the brain. So for very high cluster defining thresholds, we can get from a cluster correction a result that is then interpretable. Now, Wu and colleagues kind of took this one step further. They took resting state data, so real data that didn't have any task type signal in it, and then they created some simulated areas of real activations. Yeah. So as you can see here, these are the true signals. And then for every participant, they varied the amount of signal in every participant, so the signal to noise ratio, the amount of variance across participants. So they varied all these things, and you can see them here. And then they added noise, so that they would end up having different levels of certain amounts of within, between subject noise. And then they used the signal, as I said, was of different intensities, and then they used different thresholds and different methods. And the question is, how well when we do a group analysis, how well can we recover the actual signal, the true signal that we put in there for different thresholds and different techniques? So first, here are different thresholds. First, if you look at how big a cluster you get for each threshold, kind of as we saw with the simulations, it turns out that we get the colors are different SNRs. You can see it on the right side. For whatever SNR you tend to get, and in most thresholds, you tend to get fairly large clusters. I mean, 4,000 voxels, that's huge. If each voxel is 3 by 3 by 3, 4,000 voxels is a huge volume. And in fact, they put, for reference, they put these dashed lines which represent the anatomical, the average size of the anatomical regions within the Harvard-Oxford Atlas and within the Craddock 200 Atlas, which are fairly reasonable segmentations of the human brain. So we get clusters of these giant sizes, but the anatomically meaningful sizes and functionally meaningful sizes are probably closer to here. Unless we have, this particular signal to noise ratio and these really high thresholds, these really conservative thresholds, we almost always get clusters that span multiple areas. Second, if you look at the voxel-wise level, what is the estimated level of false discovery rate per threshold? Turns out, you would want this to be as low as possible. Turns out it's pretty high. It's 0.7. Again, it depends. It varies across the level of SNR, but it's pretty high. And actually, it remains pretty high for most thresholds. Second, how is our sensitivity, which we would like to be as high as possible? Well, that turns out generally to be pretty high, with the exception of the very sort of low SNR signal. So that is sort of that is pretty desirable overall. It turns out to be pretty high. Again, this is at the voxel level. And then what is the cluster level family-wise control of error rate, which should be 0.5, right? It should be 0.05, excuse me. We would want it to be always lower than 0.05, always rather at 0.05. Turns out, most of the time, so if you have a threshold of 0.01, which is 2.3, or I guess 2.7, which is 0.005, you still get error rates above the nominal error rate for clusters. Now, only the first one is significantly different than 0.05. So really what they say is, look, 0.01 or 2.3 as a cluster forming threshold, that doesn't work. Doesn't work. The truth is that if you look at 0.005, many times, even if not statistically so, the center of gravity of all these simulations is definitely above 0.05, although definitely not statistically so. And then also notice that the further down you go in terms of the threshold, the more conservative you get. So overall, they conclude that the primary CDT cluster defining threshold, again, how high do we put our threshold to get only a 0.5% chance of getting a significant cluster in null data, is really crucial. And it's crucial not only to getting valid data, but also to getting interpretable data. Because if a cluster is too large, as I said, and spans too many anatomical regions, it doesn't really help you, because you can't conclude much out of it. If you get liberal threshold, 0.01, so that would be a 2.3 in terms of a z-stat, that will lead to increased family-wise error greater than the nominal rate 0.05 or whatever you chose. And of course, they also say that, look, those color maps, if you color the whole cluster, you are at risk of implying to the reader that every voxel in there is active when you don't necessarily know that to be the case. So their recommendations overall, which I don't necessarily agree entirely with, is, if possible, don't use cluster correction, always use voxel-wise correction. I would oppose to that, but you should make up your mind. I would oppose that random field theory, voxel-wise, is extremely conservative and does control well for type 1 error, but exposes you to giant type 2 error, so false negatives. FDR also lacks specificity because 5% of your data, at least, 5% of the voxels you're declaring active turn out are false claims, although you don't know which of the 5% they are. So in that sense, it doesn't help you as much. This instead, I think they do make a good point. If you're looking at overlap between two tasks, finding clusters that overlap does not guarantee that there are voxels that overlap, that there are significant voxels that overlap. Again, because while you find a cluster, you don't know that all voxels in there are significant. So if you want to really do overlap between two things, probably you should be using a voxel-wise type correction. Of course, it's a trade-off. You will be suffering from other issues. For example, if you do an FDR or if you do a random field theory at the voxel-wise level. As always, it's a trade-off. If you're looking at small regions, you probably don't want to use cluster correction. Because if by any chance you get a cluster larger than that region, then you can't conclude much out of it. Maybe if you have a specific hypothesis about the amygdala, maybe you want to do a small volume correction instead, or something of that sort, or an ROI analysis, even better. However, if you do have effects of moderate size and a fairly good sample, they say 50, but I don't know if it necessarily needs to be that high, then cluster extent thresholding might offer great sensitivity. However, if you do it, you have to use a stringent CDT. You cannot use 2.3 as a cluster defining threshold. Their data suggest that you should use either 2.7, which is 0.005, or more, or higher. Even though they sell their data as implying that you have to use 0.001, which would be 3.1. But of course, the more stringent your threshold is, the more specific neuroanatomical claims you typically can make. In fact, in their words, primary thresholds more liberal than 0.001, e.g. 0.01, and they're being a bit sneaky about the result, I have to say, because they're glossing over the fact that the 0.005 did not show a statistical difference from the nominal alpha. They say is not recommended. And of course, as we will see next, it's not that simple. Whether you're using FSL or SPM or AFNI does make a difference. So just the threshold by itself is not enough to decide. I mean, you might do it that way, but the truth is that if you want to be really precise, you also ought to add to that what variance, what type of variance you're using at the group level. And finally, they do say, look, if possible, color clusters differently and be very clear that this is the cluster you get, but you don't exactly know inside those voxels which are the significant ones. And finally, they suggest don't report peaks, just report clusters, because you don't necessarily know which peaks are significant. Although here too, I would oppose that the peaks are the most significant voxels within certain clusters. So of all the voxels in there, those are the likely ones to actually be correct detections.